Good afternoon. I am Chanda Devnath, one of the PMRF fellows from Aizar Barampur. So I am the TA of this course that is named as Study Guide in Organic Retrosynthesis and Problem Solving Approach. Currently we are trying to I'm trying to get you idea about different type of name reactions by which we can plan a retrosynthesis of any compound. So we have total 12 classes. So half of the classes I will try to discuss about different important time reactions and some small molecules retrosynthesis, like how we can use those reactions to plan a retrosynthesis of any small molecule. When you get an idea about those, then we will move to some multi-step synthesis. So let's start. So initially we have already discussed about some reactions earlier. So then we move to this important discussing some named reactions. So some of them have already been discussed in last classes. So in the last class we had started about discussing the coupling reactions. So there are two types of coupling. One is homocoupling, another is cross coupling. Homocoupling means when two components combined with each other, that is called homocoupling. And when two different components combined with each other, that is called cross coupling. So there are different type of cross coupling reactions like Hake coupling, Suzuki, Sonogashira, Negishi, Yama, Stille. In all of them, in general mechanism where this halide will be catalyzed by palladium through oxidative addition, it will form this palladium complex. Then it will undergo the transmetallation with another metal complex and form this intermediate, and through reductive elimination it formed this new carbon-carbon bond. Now there are different type of cross-coupling reaction. In case of Hake, we usually use just palladium. In case of Suzuki coupling, we use palladium, that is common. Along with that, for transmetallation, we use boron. Again, next is Sonogashira, where we use palladium. Along with that, we use copper. In Negishi, we usually use zinc as a transmetal. And in case of Hiyama, we use silicon. Stille, we use tin. So all this here, the aim is different, and if you're just changing by the aim, there are different type of name reactions are there. Hake, Negishi and Stille got Nobel Prize for these coupling reactions. So there is one question from previous year. This is on Negishi coupling. So let's try to solve this. So in this reaction, what will be the P and Q? So in the first step, if you add butyl lithium and TAship, it will take a proton. Now the probability, it will take a aromatic proton. So there are three types of aromatic proton: ortho, meta and para. Which proton will be taken up? Ortho, meta, para. So in case of butyl lithium reaction, it will always take a proton which is ortho with respect to this carbon oxygen bond. Because of high electron withdrawing power, this hydrogen become acidic. Moreover, therefore it will take a proton from this ortho position. So butyl lithium will take a proton from this ortho position, generating a negative charge here, and this negative charge will again attack to this zinc chloride, and one chlorine will be eliminated and it will form a ZnCl. So it will form this complex B, and when you add this PDB3 whole 4 and this bromine allyl pyridine bromide, it will undergo the Negici coupling, and there is a formation of new carbon-carbon bond. New carbon-carbon bond. So the correct option is option B. What will be the procedure among these four to get this product from simple iodobenzene? See how we use this small reaction to prepare to get an idea about the synthesis of any compound. So how we will prepare this? So there are four options. One, they have given along with this iodobenzene, they have given this alkene, and it undergoes a Hake coupling, forming this as the product. Next, they gave this alkene, this internal alkene, and same palladium. So this is not possible because this is internal alkene. If it undergoes a oxidative addition, it should be combined through this side. So this is not what we expected. So this is cut. Next is this one. If it combined with this alkene, it would combine from this plane. Then it will give a exocyclic type of double bond. But here the product is not like that. So this is also cut. Next, they have given this alkene. So if it undergoes oxidative addition, it should combine with from this side, or so this is not the similar product which we want. So this is also cut. So correct option is option A. Okay. What will be the product of this coupling reaction? This is also a Hake coupling. Whenever there is no other metal is given other than palladium, that is called Hake coupling. If along with palladium, if any other metal is also given, that is different coupling reaction based on the nature of the metal. So what will be the product of this reaction? So in last class I have already when we introduced the coupling reaction, we mentioned the coupling reaction is a concerted type of reaction. So it's happening in a single step. Because of that, there is no chance of the stereochemistry of the double bond is usually being retained, and also we know that trans double bonds are more stable than that of the Cs. So it will combine from which side? The less bulkier side, which is this one. So it will be formation of bond between these two carbon. Now see, so this is already cut, these two, because they are not forming from that carbon. Now the question is, it will be seen or it will be trans double bond or seen that it will be E or Z. So obviously we know that E double bonds are more stable than that of the C double bond because of huge steric. So whenever there is no such controlling factor is there, it always try to give a trans double bond. So the correct option is option A. So now we'll move to the different type of we have already, I think, discussed about this coupling reaction. Then now we'll try to discuss about different type of important oxidation reactions. So there are different oxidation name reactions. First one is Kodachim oxidation, then Swan oxidation, Jones PCC oxidation, and Bayer-Villigen. All these reactions we usually being used in laboratory and company for synthesizing different important molecules. So first one is Kodachim oxidation. So the Kodachim oxidation is an oxidation reaction used to synthesize aldehydes and ketones from alcohol. This is the Kodachim oxidation, general scheme of Kodachim oxidation. So if we see into the mechanism, first NCS will combine with CS Me2S. This Me2S will attack to our chlorine atom. There will be generation of negative charge. Then that will again attack to sulfur and eliminate this chlorine, forming this NS bond. Then OH will attack to this sulfur atom and forming this intermediate. Then through a alpha hydrogen elimination, it will form a ketone. So from there, what is the limitation? So if there is no alpha hydrogen is available, if there is no hydrogen is available to the carbon center which is connected to the alcoholic carbon center, then there is no oxidation is possible. So we always need at least one hydrogen for elimination to give this ketone or aldehyde. So what will be the product of this reaction? So there are two OH. One is this one, another is this one. So it will undergo the oxidation from the reaction. You say it is dimethyl sulfide, NCS and base. So it is obviously a Kodachim oxidation. So among this OH, which one will be oxidized? Both or one of them? So as I already mentioned, there should be at least one hydrogen on this alcoholic carbon. So there is no such hydrogen is available for elimination. So this OH will not react, but this will undergo the oxidation. So the product will be, I'm just drawing this part. So there will be an oxidation of this alcohol, whereas this alcohol will be intact. Okay. Rest of the system will be also intact. So I am not drawing it. So this OH will be unaffected while this OH will be oxidized. Next is Swan oxidation. Swan oxidation is an organic chemical reaction that is used to oxidize primary or secondary alcohol to ketone. The mechanism is similar to the Kodachim. So there are different type of name reaction. Just by changing they have changed the reagents. The mechanisms are almost same. So this is Swan oxidation. Why do we use oxalyl chloride instead of NCS? Instead of NCS, we are using oxalyl chloride and DMSO instead of Me2S and again base. So this is the mechanism where this DMSO will attack to this oxalyl chloride, forming this intermediate 3. After that, through carbon dioxide elimination, it will form intermediate 4. See, it is then it will react with our alcohol, and through again alpha hydrogen elimination, it will form this ketone. Just try to notice the similarities. There is also in case of Me2S, the sulfur was itself attacking to the NCS, whereas in this case the oxygen atom is attacking, and further then chlorine is attacking to the sulfur, forming this intermediate 4. But the in general mechanism is almost similar. Next is Jones oxidation or PCC oxidation. Jones oxidation is catalyzed by chromium oxide and H2SO4. If it is a primary alcohol, it will give acid. If it is a secondary, it will give a ketone. Whereas in case of PCC oxidation, the reaction is bit controlled. So it will undergo a single step oxidation, that is alcohol, primary alcohol will stop to aldehyde, and the secondary will give ketone as similar to. In this Jones oxidation, there is always a over oxidation. After aldehyde, you can't isolate the aldehyde, it will undergo further oxidation and you get acid. This is the difference between Jones oxidation and PCC oxidation. So in case of laboratory, we usually use this PCC oxidation because they are bit controlled and we can stop and isolate the aldehyde as our product. So what will be the product of this reaction? So this is if you use PCC means pyridinium chlorochromate. So it will undergo oxidation. So this OH will attack to this chromium center and eliminate this Cl from the system. Next, as there is no alpha hydrogen is available to eliminate this ester, chromium ester, it will undergo a rearrangement where it will attack to this allylic position, and this goes here and this eliminates from the system. This happens when there is no hydrogen is available, but at the allylic position there is hydrogen is available. The next step, it will undergo the alpha hydrogen elimination. Now because there is a hydrogen is available, it will take this and this comes here. So the product will be allylic ketone. Okay. Let's go to the next one. Next is Baeyer-Villiger oxidation. So the Baeyer-Villiger oxidation is an organic reaction that forms ester from ketone or lactone. So this if you have a ketone or lactone and perform this Baeyer-Villiger oxidation by using MCPBA or H2O2, it will incorporate an oxygen atom and form a ester or a lactone. So what is the limitation? For instance, alkenes in substrate, particularly when electron rich, may be oxidized to epoxide. What does it mean? Suppose you have this type of compound, a long chain with a double bond. So if and adding this MCPP, so there is probability of Baeyer-Villiger oxidation where oxygen will be incorporated here. oxygen will be incorporated here. But there is also a probability where this double bond get oxidized. That is, this double bond get epoxidized. So there will be a mixture of product. This is a limitation of this reaction. There will be a formation of epoxide moiety. Okay, let's go to the next step. So this is the mechanism as I have told. Next we will discuss about reduction reaction. So there are various important reduction reaction. First is Luce reduction, then Barch reduction and Clemenson reduction. So first we will discuss about Luce reduction. So Luce reduction is the selective organic reaction of alpha beta unsaturated ketones to allylic alcohol. The active reductant is described as cerium borohydride, which is generated in situ to form NaBH4 and cerium chloride. So this is advantage is chemoselectively towards ketone in presence of aldehyde. Whichever is it is regioselective, whichever is less active, it will react to that one, because with the first molecule that cerium will be coordinated and the NaBH4 will react with the second one. Suppose you have in a same substrate you have a ketone and an aldehyde. You'll understand by this mechanism. Suppose in the same substrate you have a ketone and aldehyde and you are performing this Luce reduction. Which will react, aldehyde or ketone? If normally you add NaBH4, aldehyde is more reactive than that of ketone because of high electrophilicity. So between aldehyde and ketone, which will react? So in case of normal NaBH4 reaction, this aldehyde will react, but in case of Luce reduction, this ketone will react, because in the first step this NaBH4H- will attack, it will open up. Before formation of alcohol, it will coordinate it with cerium, and meanwhile this ketone will react for give us alcohol. So similarly, if you have a ketone and an alpha beta unsaturated compound, it will react with the alpha beta unsaturated ketone. So this is the mechanism. So what will be the product of this reaction? They have given this example. What will be the product of this reaction? I just give 5 seconds, just think. What will be the product? I already said that cerium chloride and NaBH4 will undergo the Luce reduction and it can reduce the alpha beta unsaturated ketone to alcohol. So what will be the product? So obviously it will undergo the first step. This is a Luce reduction reagent. So in the first step it will undergo a Luce reduction. So this undergoes a Luce reduction. The next step, they have added HCl. So HCl will take the OH will be protonated and it will transfer to a good leaving group. So now this OH will attack, because there is a one probability that OH can attack directly to this carbon, then it will form a 7-member ring and a 6-member ring fused, and that is not that, because it will be breach type of compound, so it will not that much stable. Another probability is it will attack to this allylic position and this will move here. So it will give us a 5-member ring and a 6-member fused 5 and 6-member ring, the formation which is better than that of formation of a breached 7-member ring. So it will form. Okay, so this is our product. Okay, let's move to the next name reaction, that is called Barch reduction. The Barch reduction is an organic reaction that is used to convert arenes to 1,4-cyclohexadiene. Advantage: it involves the organic reduction of aromatic ring, and Barch reduction does not reduce the aromatic ring all the way to cyclohexane. So it can reduce the aromatic ring to 1,4-hexadiene, not to cyclohexane. Like it can reduce this to double bond. This is the mechanism. This is a single electron transfer reaction where the single electron of sodium react with our aromatic ring. So this single electron will first be added to one of the carbon and it will move to form a negative charge here. Then this single electron will take another electron from sodium, forming another negative charge, and this will give us this 1,4-cyclohexadiene. Suppose you have an electron donating group in your aromatic ring or electron withdrawing group. How the electron will be added to your ring? The first electron, that is from the sodium, how will you, which put, because whenever there is benzene there is no such direction in the aromatic ring, but if you have a functional group, there is always a direction of electronic movement in the ring, so which will manipulates the addition of the single electron towards the ring. So if you have a electron donating group, the electron will be added to the ortho position of that one and it will move such a way that will get a double bond, which is one double bond will be conjugated with this electron donating group and another is just opposite to that. In case of electron withdrawing group, then the double bond will be at the alpha beta position, sorry, beta gamma position with respect to the electron withdrawing group and just opposite to that one, because here the electron will be added to this ipso position with this, you know that this is ipso, ortho, meta, para. This position is called ipso position. So whenever there is electron withdrawing group, the high electron withdrawing nature, this carbon is the most electron deficient. The first electron will be added to this position. Because of that, the double bond will be placed like this way. So whenever is the electron with donating group, just draw the double bonds like this way, and whenever there is electron withdrawing group, you have the reduction will be like this way. So what will be the product of this reaction? So they have given this benzoate ester. What will be the product? Now first we have to determine the ester group is electron donating or withdrawing. So as it looks like an acid, and due to conjugation also, this ester group acts as a electron withdrawing group. So now you can determine how the double bond will be placed. So this ester group is the electron withdrawing group. So the single electron will be added to this position, and the double bond will be placed like this and this. So the correct option will be option A. Okay. Next is Clemmensen reduction. Clemmensen reduction is a chemical reaction described as a reduction of ketones or aldehydes to alkanes using zinc amalgam. So this is the mechanism of the Clemmensen reduction, where there is a single electron from zinc is donated to this ketone, forming, and it will open up. Then this single electron zinc will combine with another zinc molecule, and through elimination of one C8 is to zinc, it will form, there will be a CH2 instead of this carbonyl. So this is called Clemmensen reduction. So now let's move to the question. So we have to plan the synthesis of this compound from this substrate. So this is the retrosynthesis sign, you know. The single arrow means the reaction is forward reaction, and this double arrow means this is a backward reaction. So this is our product, and this is our substrate. So if you think this is our substrate, and what reaction if we perform on this to get this as our product? So our options is Luce reduction, Barch reduction, Nairi, Clemmensen. So there are two carbonyl moieties which have been reduced. So what will be which type of reduction will usually use? Luce reduction we have already studied. It reduced ketone or aldehyde to alcohol. Barch reduction is to reducing the double bonds, not for the carbonyl. So what will be so it will be a Clemmensen reduction. So option D. Option D. We know that in case of Clemmensen reduction, this carbonyl group is reduced to CH2. So that's why it will be a Clemmensen reduction. Let's move to the next one. How will you plan the formation of this cyclohexane from this cyclohexene? So difference is this double bond is getting reduced. So among which of this reagent that double bond will be selectively, the double bond will be get reduced. So if you add lithium aluminum hydride, it will reduce this carbonyl group. If you add N2H4 hydrogen, it will reduce, it usually reduce the double bond, but electron donating double bond means electron rich double bond. So this double bond is alpha beta unsaturated double bond. So this is highly electron deficient double bond because of conjugation with this carbonyl group. This double bond is highly electron deficient. So the hydrogen can't react with this one. Electron deficient double bond. This is the electron deficient double bond. So N2H4 can't react with this one. Next is this Luche reduction. Luche reduction will reduce carbonyl to alcohol. So the last option is Barge reduction. So in case of Barge reduction, we know that it can react with this alpha beta unsaturated double bond. So it will react and give us this cyclohexane. So Barge reaction can reduce aromatic ring as well as alpha beta unsaturated double bond. Only alpha beta unsaturated double bond, not any double bond. Only aromatic ring, partially reduce the aromatic ring, or alpha beta unsaturated double bond. What will be the product of this reaction? This is one question from previous year NET. What will be the product of this reaction? First is divalage. So divalage will reduce alcohol. So divalage will give a H minus. It will give us a H minus. That will attack. And it is a ester group. That's why it will open up, just forming a alcohol. Okay. In the next step, they have added this Grignard reagent. So Grignard reagent will attack to this aldehyde center. Forming an alcohol. And wait here. Next, they have added PCC. They have added PCC. So you know, PCC, in case of PCC, it can oxidize both the allylic OH and this. Sorry, there is no, this is not aromatic. If there is any alpha hydrogen is available, in case of PCC it can oxidize both. So there is alpha hydrogen here and there is hydrogen here also. So both the alcohol will be oxidized to give ketone. So the correct option is option A. Correct option is option A. Let's go to next question. What will be the A and B? This is simple. First step is Barge reduction. Second step is MCP, this epoxidation. So what will be A and B? If you can determine A, B is simple. So OMe is electron donating group. Methyl is also an electron donating group. So you have to place your double bond such a way that both the factor satisfies. Both the electron donating position satisfies. Just give 2 seconds. Just try, think. Where do we place the double bonds? From the options you can see. Here it is placed with respect to this OMe. not with respect to methyl because it is conjugated to OMe. In this case, it placed with respect to both methyl and OMe because it is both the double bond is conjugated with each of this group. It is also same. In this case, it is placed with respect to this methyl group, not with the OMe. So obviously, A and D are cut. A and D are cut because they are satisfying just only one functional group, where in case of B it is satisfying both the functional group. Now next option is MCPB will undergo the epoxidation. Which double bond will undergo epoxidation? This one or this one? So we know in MCPBA epoxidation always takes place to the electron rich double bond. Whichever double bond is highly electron rich, that double bond will react with MCPBA to give us epoxide. So between these two double bond, which one is more electron rich? Obviously the double bond with OMe because of high electron donating nature of this OMe. This double bond is most electron donating. So the correct option is option B. So they have asked to form this product from this substrate through one of this reaction. So what will be the, so this is to plan the retrosynthesis from this substrate to this product. So first one is pinocol. Pinocol, it is for dialcohol system. So this is already cut. Second one is Jones. Obviously this is oxidation because alcohol is oxidized to aldehyde. So one of the oxidation. Jones oxidation is possible. Jones oxidation means the oxidation with chromium oxide and H2SO4. In that case, I already told, if there is a primary alcohol, we can't isolate aldehyde. It always undergoes the over-oxidation to give us acid as our product. So this is in both the cases we are getting aldehyde. So Jones oxidation is not possible because it undergoes a over-oxidation. So it is a cut. Baeyer-Villiger oxidation is for formation of ester, not for aldehyde. So this is also cut. So option is remaining Swan oxidation. Swan oxidation can oxidize both the alcohol, secondary and primary alcohol, because they have a H available, and it stop at the aldehyde step, not undergo the over oxidation. Because of that, the correct option is option C. The correct option is option C. Okay. Next question is, what will be the major product X formed in the following reaction? Exhibit absorption of 1765 centimeter inverse in the higher spectrum, and the structure is X. What will be the product here? So they have given PCC. So in presence of PCC, primary alcohol give aldehyde and secondary alcohol give ketone. And if there is both are present between primary and secondary, the primary is more electron rich or electron donating. Because of that, it will prone to oxidize faster rate. So let's start. So this aldehyde will be this OH will be oxidized first, and OH is there. In the next step, this OH will attack to this carbonyl, forming a 5-member ring. Next, if you undergoes another oxidation, it will give us ketone. So the correct option is option D. What will be the product on this reaction? This is an example of Barch reduction. So CO2H group is given, that is a electron withdrawing group, so the benzene ring will be reduced. Also triple bond is given. We know that triple bonds get reduced by Barch reduction. So what will be the product? So obviously the aromatic ring will be reduced such a way that there will be double bond placed at the alpha beta position, the beta gamma position. So the correct option will be between A and B. So C and D are already cut. Now the question is, there will be a double bond, trans double bond or syn double bond. In case of Barch reduction of triple bond, always remember it will give a trans double bond. Barch reduction of triple bond, always remember any factor can switch that it will always give a trans double bond. So the correct option is option A. Correct option is option A. So what will be the major product formed in the following reaction? This is also an example of Barch reduction. So there is the electron donating group and there is the electron withdrawing group. So you have to place the double bond such a way.
Ma'am, can you go back? Can you go back previous slide, please? Okay, this A is the option. Okay, thank you. Just for one.
So what will be the major product of this reaction? So there is the electron donating group and electron withdrawing group. See, in presence of Barch reduction, it will undergo this is also a question from previous, I think, recent year NET. So if we consider the electron withdrawing group, because in case of Barch reduction, there is a donation of electron to the ring. So as CO2H is the electron withdrawing group, its effect is higher than that of the OMe. So because of that, it will donate an electron to this center and give us a product like this. In the next step, they have added NH4Cl. So NH4Cl is a mixture of ammonia and HCl. It will give H plus, slightly acidic. This is slightly acidic. It will give H plus. This H plus will be taken up by this OMe. Always remember to see all the reagents. See, they are mentioned, then is NH4Cl. So obviously, in case of last whatever examples we solved from Barch reduction, there is nowhere they have mentioned the addition of NH4Cl. So that means there is a role of NH4Cl. If you just stop the reaction, then you can't go to the. See, there is no such option like this. So you'll be confused which will be reduced. So if you add H plus, it will be oxidized and become methanol. So then there is a H available which is acidic because it is adjacent to CO2H. This comes here, this double bond moves to here and removes from the system. So the correct option becomes, so we get a, sorry, so there is no such, only this double bond is shifting. Only this double bond will move to here and this OMA will be. So the correct option is this one. There is a generation of positively charged. This positive charge will be quenched by lithium. Okay, so the correct option is option 3. Correct option is option 3. So from the reagents you can see this is a Barch reduction. From the reagents you can see this is a Barch reduction. In case of pyridine, as pyridine is an electron due to this nitrogen is trivalent. Okay, this nitrogen has already 3 bonds in it. So this nitrogen will not show any Plassard effect in this ring. This ring is without the involvement of this nitrogen lone pair, the ring is already aromatic. So there is no involvement of this nitrogen lone pair. Because of that, this nitrogen will not show any Plassard effect. This nitrogen will not show any Plassard effect. Instead of that, it may show, because of its electronegativity, it shows some minus I effect. Therefore, we are considering this as a electron withdrawing group. Considering this is as a electron withdrawing group. So what happened in case of electron withdrawing group in case of this Barch reduction? I have already explained about the shortcut. So what you can do? So if you consider this is electron withdrawing group, then what will happen? Then you have to keep the electron withdrawing group and draw 2 double bond beside this. So it will be formed. Now in the next, this is the after one. Okay, this is after first step. Now in the second step they have added H plus or H3O plus. H3O plus. So because of adding of H3O plus, this double bond can be protonated and form this. So this will form. After that, due to addition of water at this position, this bond breaks. And form this. through minus H plus. From this OH. After that, this OH comes here and breaks this carbon nitrogen bond and form a ketone after the reaction. To form a NH2 and a ketone here. Similarly, the same thing will repeat at this position also. The same thing will repeat at this position also. The same three step will repeat at this position also. These three same step will be repeated at this in this case also. And after that we will get a diketone. Sorry. We'll get a diketone. Okay. Now see, at the third they have again added this KOH methanol. Whenever you see this KOH methanol and a diketone system is there, so what you will try for? Obviously aldol condensation. Aldol condensation. So if we take a proton from here and if we combine, will attack to this place and through elimination of water it will form okay. So it will what will be the answer? Option B. Option B. Understood? So this was our homework. Let's go to the next. So these are some other examples of Barch reduction. It doesn't come to the exam much, but for an idea that what will happen if we add sodium or lithium and liquid ammonia into these substrates. So I have shown these examples. So if you take this type of thio compound and add Barch reduction reagent, what will happen? This will be eliminated and hydride will be entered into the alkyl group. After that, if you take this type of thiamide, what will form? This thio group will be reduced and will get this amine from the system. Again, if we add this in this sodium amide into this tosyl amide, this part will be removed and hydride will be incorporated in the system. Okay, so these are some special examples of Barch reduction. So if we add this Barch reduction reagent into this type of special substrates, what will form? If you got an idea. Okay, so let's go to today's topic. So today's topic is hydride donor based reducing reagent. So there is most reduction of carbonyl compounds are done with this type of reagent that transfer a hydride from boron or aluminium. So here I have shown some important hydride donor reagent. First one is LiLH4, then air aluminium, LiL tertiary butyl, NaBH4, NaBH3CN, boron, AlH3, diacetyl boron, and lastly divalate. So today I will discuss some of them, the mostly used ones which we mainly use in our laboratory in a broad purpose and also in industry also. So I have taken from here, I will explain today some uses of LiLH4, NaBH4, divalate, and finally boron. So we'll discuss these 4 reducing reagents today and we'll solve some questions based on that. So these are the mostly employed reducing reagents, and in our examinations also we have seen that questions comes from these reagents in a greater amount. So next is LiLH4. So lithium aluminum hydride is a powerful reducing agent and reduces most of the commonly encountered organic functional group. Aldehyde, ketone, esters, carboxylic acid, lactones can all be reduced smoothly to corresponding alcohol under mild condition. Carboxylic amide are converted into amine or aldehyde in presence of LiLH4. So this is the in general mechanism. Where I have shown this is the LiH4 and this is the lithium salt. This H minus will be transferred to this carbonyl group, form this type of complex, and again another molecule of carbonyl group will react with another molecule of hydride and form this type of tetramer, and after through addition of water, the workup will get this alcohol in as our product. So LiLH4 can be used for reduction of all these functional groups. If we go one by one, if we add LiLH4 in aldehyde, what we will get? We will get a primary alcohol. If you want to know about detail in mechanism, you can go and check books like Claydon and all. And if you want to know from mechanism of the specific reaction which I am talking about, you can ask me, then I will add in the next class. I am not going into the all mechanism for all the questions. I have just shown the general mechanism because I think this mechanism is pretty easy and you can solve by yourself. So if you add ketone in LiLH4, you will get a secondary alcohol. If you add ester, you will again get a primary alcohol. Acid also give a primary alcohol. Amide will give a primary amine. Similarly, this one also. add LLH4 in oxime, that will also give a primary amine. If you add aromatic nitrite nitro group, it will form a hydrogen type of complex. If we add LLH4 in alkyl bromide, it will simply substitute the bromide from the system. In tosyl also it will just substitute the tosyl group. In case of epoxide, it will open the epoxide. So we are attacking at the less hindered side. So we are attacking at the less hindered side. So which one is the less hindered side in this epoxide? Obviously this part. So this H minus will attack to this carbon and open the epoxide to form this alcohol. Okay. Let's go to the next some questions based on this LLH4 reduction. So they have given this compound with the NBOC and the CH2 group. LLH4 obviously will not affect any NBOC group, but it will reduce this aldehyde, so this part will be same, just this CHO will be CH2H. I am not drawing the rest part. This part will be all same, just our aldehyde will be reduced to alcohol. Okay. Next is this LLH4 reduction. So this amine is there, so amine is in least oxidation state, so it will not be reduced further. So what will happen? Just our acid will be oxidized, reduced to primary alcohol. Next is this one. Here one amide group is there. There is no such other functional group, so this amide group will be reduced to primary amine, and from this as our product. Okay. Now, if we add LLH4 in alpha beta unsaturated aldehyde, what will happen? So, alpha beta unsaturated aldehyde are in conjugation with the corresponding aldehyde, which reduces the electron density in the ring. Because of that, we reduces the electron density to this double bond. Because of that, this double bond becomes electron deficient and highly electrophilic. Because of that, this H minus will, instead of this aldehyde, this H minus will attack to this place, and it will reduce this double bond as well as the aldehyde. It will reduce the double bond as well as the aldehyde. But if you perform the reaction at low temperature or with any other reducing agent like dival H NaBH4, in that case this double bond remain unreacted and we specifically get this carbonyl reduction. Okay, so if you in a reaction, if there is an alpha beta unsaturated group and you are adding LiLH4, both the double bond and the carbonyl will be reduced. Whereas if you perform the reaction at low temperature or with any other reagent like NaBH4 or divalH, in that case only our carbonyl group will be reduced. Next is divalH reduction. So divalH reduce the esters and ketone into alcohol. Dival on reduction of NPTEL gives the amine and epoxide are cleaved to alcohol. At low temperature, esters and lactones are reduced directly to aldehyde. Nitriles and carboxylamide gives amine, which are readily converted to aldehyde by hydrolysis. So I have shown one of the example of divalH where this ester is directly get reduced to alcohol. Without cleaving the ring. So what is happening? This H minus is attacking at this place and it's opening up to form this alcohol. So in case of divalH reduction, from ester we directly get an alcohol. From ester we directly get an alcohol. Here you can, if in case of ester, if we add divalH, we are getting this CO2Me group get reduced and we get aldehyde from the system. The next question, if you add divalH in nitrile, what will happen? This CN will be reduced. This CN will be reduced and nitrile will give a primary amine. This part will be same, just it will be a CH2 NH2. Okay. If you add the same divalH into an alkyne, it will undergo a hydrometallation and in the result through workup we will get a cis alkene. So where this through the two hydrogen group are adding at the same plane of this double bond. Okay. So if we add divalH into an alkyne, we will get a cis alkene. We will get a cis alkene. So instead of H3O plus, if you add iodine into it, what will happen? This LiLH4 Al group will be substituted by iodine and we will get this iodinized product in our system. Okay. Next is NaBH4 reduction. So sodium borohydride is a very selective reducing reagent and reduce aldehyde and ketone to alcohol. Sodium borohydride is a comparatively weak reducing agent, and because boron hydrogen has more covalent character than lithium hydrogen, it does not react or slow react in case of ester and cyclic ester. NaBH4 is a chemoselective reagent for carbonyl compound in presence of esters and amide functional. NaBH4 is insoluble in ether but soluble in alcohol and water, so it is used in hydroxylic solvent like alcohol or isopropanol, etc. So let's go to the reaction. So this NaBH4 will just similar to the LiLH4, it will just reduce the carbonyl groups, but the thing is the reducing property of sodium borohydride are substantially modified in presence of metal salt, particularly in presence of cerium chloride. So what happened if we add NaBH4 in this alpha beta unsaturated compound, what will happen? It will just reduce this double bond. As if LiLH4 is there, then both of them will be reduced, but as NaBH4 is less selective, so in this case we will majorly get this carbonyl compound reduced product, but not in the selectivity is not that high. But if we add cerium chloride, what will happen? The selectivity enhances and we get 99% of this product. Similarly, if we add NaBH4 cerium chloride in this compound containing an aldehyde as well as an alpha beta unsaturated aldehyde, what will happen in this case? Can you guess? Due to chelation of this cerium chloride with this CHO group, as CHO group is more electrophilic, this NaBH4 will react with the less electrophilic group and we will get this as our product. We will get this as our product. Similarly, in this case, there is a ketone and an aldehyde center. So, which one is more electrophilic? Obviously, the aldehyde one. So, aldehyde one will chelate to the cerium chloride. Because of this chelation, the NaBH4 will react with this second reactive group, that is ketone, and will give alcohol from the system. So, if we want to draw a overview from this reaction, that whenever you add cerium chloride along with the NaBH4, the second reactive group will react in this under this reagent system and give us our product. Okay, so whichever is the most reacting group, that will be NPTEL. Whichever is the second reactive group, that will react and give us our product. This is a shortcut. Okay, because the most reacting group is already reacting with the cerium chloride and get chelated, and because of that it get blocked. So the second reacting group comes close to the NaBH4 and give us our product. Next is boron reduction. So BH3 is a neutral reducing agent which can select for carboxylic acid reduction in presence of the more electrophilic carbonyl groups. So BH3 can reduce the acid group selectively in presence of other functional group like aldehyde and ketone. So strong anionic reducing agents such as lithium aluminum hydride can reduce carboxylic acid also, but however these reactions are not selective. Even LiLH4 can reduce the other functional group also, so this is not selective for any acid. Secondly, the less nucleophilic anionic reducing reagent such as sodium and lithium borohydride are no longer reactive towards carboxylic group. So this BH3 has come up with a very selective nature which can't be achieved by other reducing reagent. The use of more forcing conditions such as combining NaBH4 with various additive can allow the oxidation of aldehyde, but it enhances the cost of the reaction, high temperature, and most of the case we are unable to get the product. But by using any BH3 under room temperature is very easily we can reduce. By using BH3 under room temperature we can easily reduce acid to alcohol. Okay. So what will happen in this case? So as there is no such acid group, but there is a CN group is there, the CN group will be reduced and give us this primary amine. The rest part will be same, so I am not drawing it. The rest part will be same. Okay. Next is this one. There is an acid group, so acid group will be reduced to give this primary alcohol. From this as our product. Okay. Let's go to the next question. So before that, so till now I have discussed about LiLH4, NaBH4, boron and divalent. So if we want to know, draw an overview of these 4 reagents, I have tried to compile them in a one chart. So if you take an iminium ion, it will give an amine. If you take an acyl chloride by LiLH4, you will get an alcohol. From aldehyde ketone, you will get an alcohol. Ester, you will get an alcohol. And amide also, from you are getting an amine, and carboxylic acid will give an alcohol. Similarly, if you add NaBH4 in iminium, it will give an amine. But NaBH4 will not react with acyl chloride, but it will react with aldehyde and ester to give alcohol, but it will not react with amide and carboxylic acid. Again, if you take boron, it will react with aldehyde and ketone to give alcohol, and amide to give amine, and also with carboxylic acid to give alcohol. It will not react with ester and iminium ion. And in case of divalent, it will not react with iminium ion or acyl chloride, but it will react with aldehyde or ketone to give alcohol. Again with ester to give aldehyde, specifically like one step reduction, just one step reduction. From aldehyde, from amide it will give aldehyde, and again from carboxylic salt, it will give alcohol. So there is difference. If we add LiLH4 in amide, you will get a, if you add LiLH4 in amide, if you add LiLH4, you will get a primary amine. But if you add divalent, you will get a aldehyde. Okay, so you can, from the chart you can get a short overview of all the reagents. Next class I will try to discuss the other ones. Mostly whatever questions you get in your upcoming NET or GATE, in those examinations they usually include the questions from this reagent. These reagents are also being used, but not in large number. And the reactivity, if you know the reactivity of the NaBH4, you can also kind of predict the reactivity of others, the NaBH3CN and all. Okay, so let's go to the previous year questions. So they have given this product and added LiLH4 to room at low temperature. What will happen in this case? So LiLH4 With alpha beta unsaturated compound, what will happen? It will attack to this beta position. It will attack to this beta carbon. Now this methyl is already above the plane. So allyl H4 will come from the below the plane. So allyl H4 will come from the below the plane. As methyl is already above the plane, the hydride will come from the below the plane. This goes here. On addition of Ac2O, sorry, LLH4 will just reduce this carbonyl group. As it is happening at the low temperature, I have already in the previous examples I have told, if you perform the reaction at room temperature, the double bond as well as the carbonyl will be reduced. But as the reaction is happening at the low temperature, only the carbonyl group will be reduced and give us this alcohol. Now if you add Ac2O, you will get OAC. Now as Me2CuLi is added, so you can consider this as a ester. So it will attack to this position and it comes up here and OAC will be removed from the system. Now as methyl is already above the plane, it will come from the below the plane. So this is after reagent step 1, step 2, and this is after step 3. So methyl is already there, so the new methyl will come from the below the plane. Double bond will shift here. So methyl is coming at this base, double bond will shift here, and OAC will be removed from the system. We will get this as our product. Option C. Okay. Let's go to the next question. Identify the appropriate reagent for A and B for following reaction. So you have to identify the appropriate reagent for A and B. Now, how the product of A will be formed and how the product of B will be formed. First we have to get that, then we can choose the reagents. So from here you can see a cyclization is getting performed. In A, this carbonyl is present at this part and there is no such carbonyl. So that means in case of A, this ester will be reduced to alcohol and this alcohol will attack to this acid to form this lactam ring. In case of lactone ring. In case of B, see there is a carbonyl group but there is no such carbonyl group. That means this acid group will be reduced here and attack to this ester group and form this lactone ring. Now, so that means we have to, in case of A, we have to specifically reduce this ester group. In case of A, we have to specifically reduce this ester group, or in case of B, we have to specifically reduce this acid group. So you have to choose the reagent. If you add LiLH4, what will happen? both of them will be get reduced. So LiLH4 is cut because if you add LiLH4, both of them will be reduced and give alcohol. So LiLH4 is cut. So whichever having LiLH4 in their option, that is cut. So this A and B is cut because LiLH4 will reduce both of them. Now next is, we know to reduce acid specifically, reduce acid specifically in presence of other group, we use boron. We use usually boron. So for B we use boron. So B as a boron, there is a boron. So the correct option will be option C. And LiBH4 is less reactive than LiLH4, so that will selectively reduce our ester, and whereas the boron will selectively reduce our acid and we will get A and B. Okay. I hope it's clear. Let's go to the next question. So this is based on the theory, the concept we discussed in the last class. I couldn't, I missed this question. So today I have added this one. So this is based on Barch reduction. So if you perform the Barch reduction for, this is a electron donating group. This is a electron donating group. Electron donating group. So if we go by our shortcut, the strategy I have. So we'll just draw the double bond at this, like this way, where the OMe is there. Now in presence of H plus, this ether will break and it will be hydrolyzed to give OH. That undergoes tautomerism. And to get a conjugated structure, there will be a double bond migration. There will be a migration of double bond. We will get D as our product. Okay. At your home, I will discuss this topic in the next class and we will solve this question. Just for instance, you can try by it yourself. In the first, they have asked for what is reagent A and B. In case of A, this allylic double bond is getting cyclopropionation, whereas in B, this alpha beta unsaturated double bond undergoes cyclopropionation. So by just varying the reagent, we can get two products. This is called regio selectivity. This is called regio selectivity, because both the double bonds are in different nature but in the same system. Just by changing the reagent, we can react one of them. So let's give a recap of today's class. So first, we are discussing about different name reactions. So as we started about coupling reaction, we start talking about coupling reaction and in general mechanism of that one. Then we solved a question from on this coupling reactions. Then some many more. Then we moved to oxidation reactions and discuss some important oxidation reaction like Korekim, Swan, Jones, PCC, Bayer-Villiger. Then we solved questions. Then we discussed about some reduction reactions like Rulce, Barch and Clemenson. Whatever reduction or oxidation I have discussed, these are the important ones, and in your assignments also this reduction reaction has been mentioned again and again. So I have just picked those. Then we discuss about that. Then we solve some questions. Okay. So thank you everyone. Uh, we'll meet in the next class where we'll discuss about annihilation reaction, different type of annihilation reaction, and how we can use those to get an idea about retrosynthesis of any compound. So thank you.
Hello, ma'am.
Yes.
I checked the drive, but you did not upload your slide, your presentation slide everyday classes. I missed two classes, so that's why repeatedly I'm asking you.
Okay, sorry. I just forgot. I will upload it today.
Okay, okay, okay. No problem, no problem.
Thank you.
Okay. Thank you so much.